Okay, so I want to make a video kind of going through the tables and formulas that I've given to all of you. I mailed you a copy of these tables and formulas. So let's go through this just to kind of familiarize ourselves with what the rest of the class is going to be like. So let's do this. And this is the formulas that I've given you. The first page we've been using when we do our normal calculations. Right, we've used this table a lot so far, and this is for our standard normal calculation. So we have been using this table. When we start with confidence intervals, using the t distribution, that's where this page comes in. This is where you're going to find your t critical values up here, t critical values. Again, these numbers are a little light, but I'm pretty, you can read all of these and you can make it out. These are the best tables I could find. I have another one here of this same idea for t distribution critical values. I'll post this one also online. This is the same information as this. This gives us degrees of freedom here on the left-hand side and levels of confidence across the top. And as the sample size increases, remember the degree of freedom is one less than the sample size. You can see as the degrees of freedom increase, this last row here are the Z critical values for the appropriate confidence intervals. Remember we said 90% confidence, 1.645, 95%, and 99%. We also have other ones here, 98, 99.8, and 99.9. But this table gives you the same information as this one. Just here, 90% is we call 0.10 for 90% confidence would be the 0.10 column. 95% confidence would be the 0.05 column. And 99% confidence would be the 0.01 column. And again, notice down here, the last row, for 90% confidence, I guess we got the confidence intervals down, or the levels here, also at the bottom, 1.645, 1.96, and the 2.576 that we have been using mostly. But as you can see, we have several other confidence levels. And like we said, we can find whatever confidence level we want in our standard normal table, depending on what Z values cut off that appropriate percentage. So we haven't used these next few pages yet. This is what we're going to be introducing when we start talking about hypothesis tests. So these are t-tables, and we're going to use this very similarly as we use the standard normal table to find probabilities once we establish areas under this curve. This is called the student's t curve. Notice it's still a bell curve. And I think we mentioned before, the t distribution is a little flatter in the middle than the bell curve and has more areas at the tail ends. And we will learn how to use this table as we move through the next few sections. The degree of freedom column is here on top. This goes 1 to 12. And these are the t values, just like we did before looking up z values. We look up t values. T values only go to tenths in this table, where the z values went to hundredths. And this table gives us probabilities to the right of the t critical, or the t value that we're looking up, as opposed to the z critical values, remember, which gave us probabilities to the left. So you have to be careful about reading these tables. We will go through this as we move along. Now this t table has several pages because of all the degrees of freedom. First page is degrees of freedom 1 through 12. The second page are degrees of freedom. Oh, look, it's degrees of freedom 1 through 12 again. So that just showed up twice. This is exactly the same page as this. I don't know how that happened. But we go to the next page and we see 13 through 24. And we see the next page, 25 up to 40, then 60, then 120. And so on. So these are the tables we're going to use when we perform hypothesis tests on means when we don't know the population standard deviation, just like with confidence intervals. So what I want to concentrate on here, and here you have all the formulas, right? So for proportions, this is everything you need. These tables have everything you need for the rest of the class. We've already talked about the formula for the confidence interval for a proportion and the appropriate z-critical values. And we already talked about the sample size calculations for desired margins of error. Here we're using B for the margin of error. I used E, I believe, in my video, but that's what we're talking about here. And again, like we talked about in that previous video, if we're not given an estimate for the population proportion, we use 0.5 in this formula. Excuse me. Now we'll get to these formulas as we move through the hypothesis test section. This first, well, I guess we should just look at it anyway. Well, let's go through the steps of the hypotheses tests first, and then we'll deal with formulas. Means, again, we've talked about the confidence interval for means. We've looked at this formula, appropriate z-criticals. And we said if we don't know the population standard deviation, we substitute with the sample standard deviation and use t-criticals in our confidence intervals instead of z-criticals. And we went over this sample size calculation, sigma z-critical over the desired margin squared. We talked about all that. We'll get to these values as we go through our sections. Difference between two population proportions, we'll get to that. Difference between two population means, we'll get to that. What I really want you to understand is the reasoning behind a hypothesis test. So I'd really like you to read through this section here of hypothesis testing. I wrote this myself, and when I was learning this, I realized that every hypothesis test that we talk about is really just a 4-step process. So it's convenient to remember these 4 steps. So I really need you to read through this. I don't want to take, a half an hour and read through this with you, but read through this. Everything is as clear as I could possibly make it. What you really want to remember is the 4 steps. Basically, the first step is, what are you looking for? And another thing I want to mention is, think about, in the USA, we have a justice system that supposedly works on the premise that everyone is innocent until proven guilty, right? That's the premise. Innocent until proven guilty. That's really a hypothesis test, right? So when we formulate a hypothesis, we are going into the test with an idea, right? We're saying, I think the average of all my students in statistics, I think the average is 80% on the last test. Right? So I go in with that idea. That's my idea going in. We call that the null hypothesis. Okay, that's what's going in. Think of innocence in the jury situation as the null hypothesis, the idea going into the test that you're going to accept unless you are shown overwhelming evidence to change your mind about that idea. So the guy is innocent until he goes into the trial, and then the prosecution comes in and says, well, this guy says he didn't murder this guy, but we have a picture of him with the knife going into the guy's body. So if he's innocent, why is all this evidence going against him? Maybe the null hypothesis is not correct. Maybe the evidence points to the alternative hypothesis, which is something else. Is it less than the average score that I thought, more than, or just different in any way? So those are the 3 different alternatives. So H sub 0 we call the null hypothesis. So when we're talking about, we'll concentrate on means here. So the null hypothesis can take one of 3 different forms. We can go in, this is the null hypothesis, H sub 0. This is the alternative hypothesis, H sub A. So we go in thinking that the population mean, we don't know what the population mean is, but we go into the test thinking that it equals some value. Okay, we go in thinking that the mean is some value. We go in thinking the defendant is innocent. The alternative can take one of 3 forms for means. Either we don't know what side we're looking on. We don't know if we're trying to show that the mean is larger than some value or smaller than that null hypothesis value. We just want to know if it's not equal to that. So that's one form of the null hypothesis. If we have an idea that it's less than what we thought, then this is the alternative hypothesis. If we have an idea that it's more than what we thought, then this is the alternative hypothesis. So you form the hypothesis first, innocent until proven otherwise. Same thing with proportions, right? We go into the test thinking the population proportion P is some value. We're going to call P sub 0 the hypothesized value. Mu sub 0 is the hypothesized value of the mean. P sub 0 is the hypothesized value of the population proportion. We don't know what the population proportion is or the population mean. That's why we're performing the test. So that sometimes is the most challenging part of a hypothesis test, figuring out what the question is, what you're trying to show. So once again, you go into a test with an idea about a mean or a population proportion. You're going to stick with that idea unless the evidence that you see, which is going to take the form of a sample, we're going to take a sample and we're going to say, do the results from the sample agree with our null hypothesis? Does it make sense? Does this sample result make sense if our null hypothesis is true? And we're going to have numerical measures of what is enough evidence and what isn't. But until we're shown overwhelming evidence against the null hypothesis, we're going to stay with it. But if we have overwhelming evidence, again, it will be numerically determined. If we have overwhelming evidence to suggest that our null hypothesis is not true, then we're going to say, we're going to go with the alternative. Right? So our evidence is going to take the form of a test statistic. Right? So after forming the hypothesis, we're going to take a sample from that population and create a sample statistic. Right? Either X bar, sample mean, or P hat, sample proportion. Right? So remember, these are sample statistics estimating these unknown population parameters. And then we're going to look at the sampling distribution of that sample statistic. And basically, we're going to say, how surprising is our result if our null hypothesis is true? All right, so our test will be based on the sampling distribution of the sample statistic, again, which is the distribution of the sample statistic if we were to theoretically take an infinite number of samples of that same size from the population. Right? And then we're going to look at it. And we're going to base our test on the distribution, because if the null hypothesis is true, then the value we hypothesize under the null will be at the center of that sampling distribution. Right? So then we create what we call a test statistic. Now, the test statistic is not the same as the sample statistic, but it's rather a standardized version of the sample statistic that allows us to use already established tables, the tables we just looked at, to find out how surprising our result is. And it's always going to take this form. You're going to have a point estimate, which is either X bar or P hat. You're going to see the difference between that point estimate and what you think the value of the population parameter is, and you're going to divide by the standard deviation of that sample statistic. Remember, sometimes we called that the standard error of the sample statistic. For tests concerning population proportions, the test statistic will be a Z statistic, always. It's always going to be a Z statistic from a standard normal distribution, and it has this form. The Z statistic has this form, the sample proportion minus the hypothesized value over this standard error. Now notice here, it's a very important difference between this expression and the expression we used for the confidence interval for proportions. When we talked about confidence intervals for proportions, back here, we used P hat under the square root sign. So notice this is a very important difference. When we're talking about a confidence interval for the population proportion, we're using the sample proportion here and 1 minus the sample proportion underneath the square root sign when we form our confidence interval. But when we go to hypothesis tests for proportions, we're going to use the hypothesized value here. So notice that it's a very important difference. When you're forming a z-statistic, you're using the hypothesized value. When you're forming a confidence interval, you're using the p-hat value. All right, when we talk about a z-statistic for means, again, same basic form, sample statistic minus hypothesized value over the standard deviation of that sample statistic. All right, so we form that z-statistic. And again, if we don't know what the population standard deviation is, we use a t-statistic. And it takes this form. Again, same general form. Sample statistic minus hypothesized value. The thing that changes is the standard deviation of the sample statistic. If we don't know sigma, we have to use S, the sample standard deviation. And so our standard deviation of the sampling distribution becomes this expression. And then we're going to find what we call a p-value. This is going to be, again, if you read this through, this is going to be the probability of finding something as extreme or as surprising or more surprising than what we find in our sample data, given that the null hypothesis is true. So basically, again, go back to the jury, the trial by jury. We're saying we're going into the trial with a presumption of innocence. Okay? And now we look at the evidence. If the evidence says, well, damn, there's a lot of evidence saying that this guy did commit that crime. There's tons of evidence. We got video, we got eyewitnesses, we got cameras all over the place. We can see it happening. So our null hypothesis doesn't make any sense given the evidence. So that's what's going to change our mind, right? The probability of finding something as extreme or more extreme than what we find in our sample data, given that the null hypothesis is true. Right? How surprising is our result? In other words, if the null hypothesis is true, how surprising is our result? And depending on the distribution being used, the p-value can be found by determining the appropriate test statistic, either a t-statistic or a z-statistic for means, always a z-statistic for proportions. And we'll do several examples of this so you can see what's going on. So when we find the p-value, and then we make a conclusion based on how much evidence we decide that we need, right? And we call that a level of significance, and that's a Greek letter alpha, okay? That's not a letter A, that's a Greek letter alpha. And again, we use the same 3 basic confidence levels. A 90% confidence level is an alpha level of 0.10. A 95% confidence level is a 0.05 alpha. A 99% confidence test or level is going to be a 0.01 level of significance or alpha. Right? And then very, very easily, we make a conclusion based on our p-value, which we're going to find from our tables. And if the p-value is less than our level of significance, then we say that's enough evidence to suggest that our null hypothesis is wrong. Otherwise, we do not have enough evidence to suggest any change, and we accept the null hypothesis. So again, just like a trial by jury, finding someone not guilty doesn't mean that they are innocent, right? It means there isn't enough evidence to prove guilt. So we're going to stay with the presumption, the null hypothesis of innocence, right? So we go into a test with an idea. We look at evidence in the form of a sample data. We use the sampling distribution of that sample statistic to come up with a level of probability that our null hypothesis is true given the evidence. And then we make a conclusion based on those values. All right, so if I really suggest that you read through this carefully, you go through these tables, or not the tables, but go through this part here, read about hypothesis testing, and our next video we will perform some hypothesis tests.